All right, let's take a look at phase changes and heat. Specifically, we're going to look at what happens to potential and kinetic energy during these changes. Now, all phase changes are always going to be a physical change, and that's because you're not changing the identity of the substance when you go from a solid to a liquid or a liquid to a gas. Instead, you're just changing the arrangement of the particles inside of that substance. And then these changes can either be endothermic or exothermic, depending on if heat's either being released or absorbed. For a system, if heat's exiting the system, it's going to be an exothermic, exothermic change. And if the heat is going into the system, it's going to be endothermic. Heat is going in, endo. So it just depends on which way the heat's moving. So we can see that there's 6 different changes that we can pretty much describe. And you can see that we can use either endothermic or exothermic to describe that system based on if heat's leaving or entering that system. Now, we can also draw a graph that represents these different changes. So as a substance changes phase, as it changes states of matter, the graph is going to show some characteristic features. For example, there's going to be plateaus, flat regions of the graphs that are going to be representative of the phase change boundary line, that temperature at which that substance is going from a solid to a liquid or a liquid to a gas. These flat portions of the graphs are going to be a characteristic where the only kind of energy that's changing is potential energy. And then the sloped portions of the graph, or the diagonal portions of the graph, that's going to be where the important change for us is going to be the change in kinetic energy, energy of motion, for kinetic energy, and energy of position, positional energy for potential energy. Stored energy is another way to look at potential energy. So we have flat regions of the graph, that's going to be potential energy, change in PE, delta PE, and diagonal regions of the graph, which are going to be delta KE. Looking at these different particles, we can see that there's arrangements of these particles, and the arrangements talk about the properties of those states of matter, and then also what's happening with the kinetic and potential energy. So as the particles are tightly packed, we have a solid, and because they're so tightly packed, that explains the behavior of its rigid shape, and its volume doesn't really change. And the position of those particles is very close together. So if I were to take a rubber band, it's kind of like my fingers right now, they're relatively close together. There's not a lot of stored energy. As we add heat to that system, so this would be heat going in, those particles are going to move further apart, and that's where we get to the liquid. You can see the particles are a little bit more spaced, but specifically they're able to flow past each other, which explains the fluid properties of a liquid. Finally, a gas, as we add more heat to that system, the gas particles are even further apart, and we need to position those particles to a greater extent. As the heat is added, the particles can move, and the potential for them to release energy gets higher and higher. So positionally, potential, position, energy, the particles are far apart, and this rubber band represents the stored energy. As heat leaves, as it's exiting, the particles are going to get closer to each other, releasing some of that stored energy. We can show how this all looks on that phase change graph. You can see there's distinct regions. If we're looking at the graph, it's time on the x-axis and temperature on the y-axis. So we have flat portions of the graph, plateaus, horizontal, and then we have the diagonal portions of the graph, and then they're all labeled with delta KE or delta PE. And we were saying that delta PE is the only kind of energy change that's occurring at the flat portion of the graph, the plateau. So delta PEs. But then we have delta KEs on the diagonal. This is where the kinetic energy is changing. Delta PE is also listed on the diagonal, but for us the important is the delta KE. At a flat part is where the phase change is going to occur. So on this portion, the diagonal portion, it's a solid. Then we're having the melting phase, so there's going to be both solid and liquid found in this system. And then once we get to the very end, as time continues, right here is where all of the solid has melted and it's starting to turn back in, and it's only liquid in that system. So only liquid, temperature of the system's increasing, hence the change in KE. Once we get to the next plateau, KE doesn't change. Temperature doesn't change at this point, because the energy that's being added is being used to stretch out those particles, to expand that rubber band. So mostly liquid, and then the quantity of liquid decreases till you have only gas. And then as the gas goes up, as the temperature goes up, the particles also can get further apart, the delta PE, but mostly delta KE here, at least for our class. And that's because the temperature is now increasing and we only have a gas in that container. Endothermic changes as you heat, exo as you release energy and the temperature goes down. Notice that the flat portion of the graph for the cooling is the same temperature as the flat portion of the graph for heating. So boiling and condensation point, BP, is equal to CP. And then the melting point and freezing point are the exact same temperature. They're the exact same as the opposite side of the graph. So that's it for heating and cooling curves. You should be able to draw a graph and label all these points on this graph, including the delta KE, delta KE, delta KE. Flat would be delta PE, no temperature change, delta PE, no temperature change. And then that this would be a solid, solid liquid, liquid, liquid gas, gas, or vice versa going down the cooling curve.